first of all, I would be very happy if you interrupt me at any point and ask questions. As you've probably already seen, there are many different ways of presenting the dynamics, the horocyclic dynamics on hyperbolic surfaces, different viewpoints, different notations. So definitely stop me if I'm using a notation which is different from the one that you saw this week. And just stop me at any point with questions. I hope that's possible. Okay, so let's start with notation, because I know that this could be a confusing issue. So the first thing we're going to talk about, everything is going to happen in the group G, which is the group of orientation preserving isometries of H2. So I'm going to denote it by G. This is the group of real valued Mobius transformation, so PSO2R. And you know that this acts freely and transitively on the unitangent bundle of the hyperbolic plane. So actually I can identify this group with the unitangent bundle of the hyperbolic plane. So again, already here, there are several notations that might be different from the ones that you've seen. So again, stop me if I'm using something confusing. This is all the same, just different notations. Okay, so I'm going to be identifying the unitangent bundle of hyperbolic plane with this group G. So a point in direction is going to be G. And now on this unitangent bundle, you know that you have two flows. You have the geodesic flow. I'll do this quickly because you've seen this already. There's the geodesic flow, which flows at time t at unit speed along the geodesic tangent to the point in direction. So this could be a point ATG. This is my notation for the geodesic flow. Sometimes this is GT. But again, I hope this is not confusing. Stop me if it is. So this is the geodesic flow, and this corresponds to multiplying. So again, this point. Oops, just a second. Yep. So this point here. This point here, I'm simultaneously thinking of it as a point in direction, unitangent bundle of hyperbolic plane, but also as an element of this matrix group. So I can consider this point at time t along the geodesic as multiplying by the matrix AT, which is this diagonal matrix, e to the t over 2, e to the minus t over 2. And again, you've probably seen this, but this is my preferred viewpoint. So this is one flow you can consider. And another flow is the horocyclic flow. So this is a flow which takes the point in direction G and translates it along a circle. And this corresponds to another one parameter subgroup, which is the lower unipotent matrices, 1S1. So again, I hope that everything so far is okay. So we have two one-parameter families of matrices which act on the unitangent bundle of the hyperbolic plane. And now we can consider, so given a discrete group, subgroup gamma of G, one can consider the quotient of the unitangent bundle. So take mod gamma, you can consider the quotient of the unitangent bundle of the hyperbolic plane with respect to this discrete group, and you will get the unitangent bundle of a hyperbolic surface or orbifold. Let's put that aside. But this is now going to be, this is going to be a surface sigma, or rather a unitangent bundle of a surface sigma, which I can also think of as, this coset space, G mod gamma, or homogeneous space. And again, if you have a point G, you have this point G in the unitangent bundle, you can project it mod gamma to a coset, and I will denote these cosets by sort of square brackets G. So this is now a point and direction in the unitangent bundle of the hyperbolic surface. And the same two flows that you have on the unitangent bundle, you can consider on the surface itself. So you have this geodesic flow. Yeah, does something. And you also have the horocyclic flow. And the horocyclic flow on this homogeneous space or on the unitangent bundle of the hyperbolic surface, this is going to be what we will consider. So maybe I'll just, again, recall my notation. This is going to be NS acting on this coset or this point and direction in the surface, bracket G. So far, okay with notations? Do you have any way to respond back to me?
Fine.
Yeah, okay. So good. So you've discussed the limit set of a group gamma, and you've discussed limit points. So again, just continuing with notations, if I have a point in direction G in the hyperbolic plane, I can look at the endpoint of its geodesic, and this is going to be G plus, so denoted by G plus. And we're going to be talking about particular types of limit points, which you've mentioned, which are spherical limit points, and talk about their relation to horocycle orbit closures and how we can use this classification or this relation to understand horocycle orbit closures in geometrically infinite setting. Good. So this was setting. Now let's talk a bit about for spherical limit points. Okay, so let's just recall. Now you've seen this definition, I'm told. So a limit point C in the limit set of gamma or the boundary of the hyperbolic plane is called or spherical. If gamma z, so you can look at the orbit of some point z in H2, look at the gamma orbit of some point, enters every horoball based at C. So yeah, so again, I was told that you discussed this, yeah, this is for some, yeah, for some z, for some or any. It's equivalent point z in the hyperbolic plane. And right, what I'm aiming towards is the following. So theorem. This is a theorem due to Eberlein and extended by François Delbo. So I will make some simplifying assumption. So assume, for simplicity, that gamma has a full limit set. So lambda gamma is just the entire boundary of the hyperbolic plane. Then, if you look at, then the horocyclic orbit of the point G in, let's write Yeah, let's write T1 H2 mod gamma on the surface. Right, this is another way to write T1 sigma. Is not dense in T1 H2 mod gamma if and only if the limit point G gamma is not horocyclic. Okay, maybe I could have stated it the other way, that a horocyclic orbit is dense if and only if the limit point is horospherical. Yeah, is there a question?
Yeah, a question.
Yeah.
In the negative form. Why do you state it in the negative form? I mean,
yeah. No reason. So that's a good question. I don't know. I try to be a positive guy. I don't know why. Well, the thing is that
okay,
I can definitely erase it. So I think this is okay. It is dense if and only if horospherical. The only reason is because I'm already interested in the non-full orbit closures. I want to describe those orbit closures which are not everything. Those are the more interesting ones, and that's why my head was going in that direction. But you're right. Let's state it in the positive. Thanks. Keep asking questions. Good. So I want to explain this for a while, and then we'll go on to see how we can use this to actually analyze orbit closures in Zika. Let's spend a while understanding this. So first of all, I want to introduce another definition. Geodesic ray. So it's denoted AT bracket G. So this is a geodesic ray on the surface on T1. Yeah, H2 mod gamma is called quasi-minimizing. Quasi-minimizing. If there exists a constant C, non-negative, such that for all non-negative T, the distance in the manifold, in the surface, between ATG, so the point at time T along the geodesic, emanating from the point in direction G on the surface, the distance from that point to G is at least T minus this constant C. Let me try to draw a picture. So, I don't know, I might have a very weird surface. And maybe there's some genus here. So this is my hyperbolic surface, geometrically infinite. And now I have a point. So point in direction bracket G. And I'm considering the geodesic ray. So I'm saying that the geodesic at G is quasi-minimizing. If you follow it for a while, it might wind around, do something, but eventually going to shoot out to infinity at essentially the fastest rate possible. So what do I mean by this? Notice that my definition for the geodesic flow was at unit speed. So this distance here is always smaller or equal to t. You cannot, at time t, you can't be more than t away from the point you started. But my request is that at time t, so this is maybe the point, hope you can see this well. This is the point ATG. I want that the distance between this point and the base point that I started with is always at least t minus some constant. So additively, up to an additive error, I want the geodesic ray to be escaping to infinity at the fastest rate possible. And this is what I call a quasi, I didn't call it, others called it before me, but this is called a quasi-minimizing ray. Any questions about this? So this is going to be very essential to our understanding of horocyclic. Yes, yeah. Thank you. Yeah.
Do you have an example of a ray that is going to infinity but with a lower speed?
With a lower speed? Yeah, many. So
yes.
Geodesic, right. That's a good question. So first of all, there are geodesic rays which recur to a compact set.
Yes, precisely. Going to infinity.
So then they don't escape to infinity at all. But essentially, geodesic rays can do whatever you want. You can always connect geodesic rays and make them do as you wish. So there are geodesic rays which escape to infinity at every rate up to this full speed. You could just make them at every point, make a stop and maybe loop around some closed geodesic and then continue for a while and then loop around and continue a while and loop around. So yeah, was that, did that answer the question?
Yes, actually, for example, if a group is finitely generated, then either the geodesic ray stays comes back, is recurrent, either it escapes with linear speed, which means that if you want to do this,
right,
you need an infinity generation. You need to add generation.
Oh, right. So if I understood the question, you're saying in the geometrically finite setting, you actually have a dichotomy. Either the geodesic ray escapes to infinity at full speed, or it recurs.
Something like this.
Yeah, so that's actually true, and that's a classification of geometrically finite surfaces, and that is actually exactly the reason why you only have one orbit closure, essentially one orbit closure for geometrically finite surfaces. So I'll get back to that. But this discussion is interesting, mostly interesting when you have geometrically infinite surfaces. For those surfaces, you have quasi-minimizing rays which do not escape for a parabolic point or outside. Yes?
I would like just to ask a tiny question. When you start from G, and you hit the boundary of a small hole, how do you get out of there? Because it is in the boundary, so you cannot get out of there. You can reach it, you can get out of there easily.
So do you mean this hole?
Well, that's it. When you hit the boundary.
Okay.
You don't get
so
inside.
My picture.
How do you move out of there?
Oh, yeah. So my picture.
So you never hit it. But as the way he draws it, it looks like you hit the small boundary and move out of there, and to carry on exponentially outside the fluid.
So this is not a boundary, actually.
Or you just close it.
It's not a boundary, so
you never hit it. You just go round and round and then move away. Okay, all right.
Yeah. So my picture might be confusing, and I don't know if you see it well enough.
I have a question here.
Wait, was that question answered? So this is not a boundary. This is like when you have a donut. This is my notation of like eye of a donut.
When you write d sigma in that definition, do you mean the distance of the foot points, or do you mean the distance of the vectors on the unit tangent bundle? Good
question. So actually, since we're talking about 2 points on the same geodesic, it's going to be the same distance. That's a good point. That's one way to avoid answering the question. So you can think of the distance between the base point or the distance between the vectors. But again, since they are both on the same geodesic, it's going to be the same distance.
Okay.
That's a good question. Or another way to circumvent it is to say, in any case, I'm looking at the distances up to constant error. So maybe this error is just going to be resolved. That was a good question. I kept it vague. Other questions?
No.
Yeah. Good, thanks. So this is going to be a really a fundamental thing to work on, because these quasi-minimizing rays are exactly exactly correspond to a non-horospherical limit point? Question? So lemma. So ATG is quasi-minimizing if and only if the limit point G plus is non-horospherical. Non-horospherical. So I don't really want to give a full picture, but I'll try to convince you. So I won't give a full proof, but I'll try to convince you with a picture. So you have this point in direction G, and now you have the geodesic ray. So I'm taking this geodesic ray on the surface and I'm lifting it up to the universal cover. And now, what does it mean that it's quasi-minimizing? The fact that it's quasi-minimizing means that if I look at time t, so this is now ATG, if I look at time t, I do not see anywhere around the large ball, so there's a ball of size t minus c radius ball around this point, where I do not see any copies of G. I do not see any gamma orbit. So this is, let's draw the gamma orbits. So this is gamma G, oops, the other way, G gamma, G prime gamma. So these are different copies of G. But since I'm saying that there's a big ball around this point, so this is going to be a ball of radius, t minus c around the point ATG, I do not see any copies of G gamma within this ball. If I were to see copies of G inside this ball, that would exactly tell me that the distance between ATG bracket and G bracket is smaller than this radius. So does this make sense? Just what I'm saying here?
Yes.
Okay. So now, as you take t larger and larger, now think of a point very far away, this ball is going to be very large. So it's going to be a very large hyperbolic ball. And as you make these balls larger and larger, they converge to horoballs. They actually eventually are going to converge to a horoball based at G plus, based at this point G plus. And this horoball is going to completely avoid all the gamma orbits. And since you found a horoball which completely avoids the entire gamma orbit, that exactly is the negative of being horospherical. Horospherical limit point is a limit point where all horoballs contain some copy of a base point.
We don't expect to see this when the group is geometrically finite, right?
Yes, so geometrically finite groups do not have non-horospherical limit points, except for parabolic. So geometrically finite groups have non-horospherical limit points, and those are parabolic points. So they are points which are fixed by a parabolic isometry. And yeah, if you think about it, you will not have, right? You will not have copies of a base point within some horoball for that parabolic limit point. And another way to think about it too is that if you shoot a geodesic through the cusp, you can make it escape to infinity at unit speed. You can make it escape to infinity as fast as you like. So a cusp could correspond to a quasi-minimizing ray. And again, therefore, it's non-horospherical. Does that make sense?
Okay, that makes sense. Thanks.
Yeah. But that's again a good comment that most of this discussion has content when you consider geometrically infinite surfaces. I'll comment about that later. Good. So if I want to rephrase Eberlein and Dalbau's theorem, in order to find interesting horocycle orbit closures, so if in order to find horocycle orbit closures which are not everything, you need to find quasi-minimizing rays, right? You need to find G pluses that are non-horospherical. And those would correspond to quasi-minimizing rays. Maybe this is very useful, so I'll write it down. Corollary. So I'll write it like this. Okay. So yeah. Okay. You know what? I'll write it the way I prefer. So you have NG. So this is my notation for cyclic group. So N is this one parameter subgroup of these NS. So what is this? NG is the horocycle orbit of a point, of the point G bracket on the surface. So this bar, the closure of the horocycle, this is not everything. This is not T1, H2, what gamma, if and only if ATG is quasi-minimizing. So this I do want to state in the negative, because again, I'm interested in the interesting horocycle orbit closures, those that are not everything. Does this corollary make sense?
It means when you have full limit set, maybe. When the limit set is full.
Okay.
When the limit set is full. When the limit set is full.
Yes. When the limit set is full. Yes, I did have the simplifying assumption. I don't want to talk about the non-wandering set. Thank you. Yeah. So under the assumption that lambda gamma. Yes. Thank you. Yes, I have this simplifying assumption. Otherwise, I would need to replace this full unitangent bundle with what's called the non-wandering set for the horocyclic flow, which I just want to avoid discussing. Yeah, it won't be relevant for the Z-cover case. I mean, in the Z-cover case, this is the relevant formulation. So maybe just one thing to note, so remark, what does this corollary tell us? It tells us that if a horocycle orbit closure is not everything, then it only contains so points with quasi-minimizing rays. You can't have a non-full horocycle orbit closure contain a point whose geodesic ray is not quasi-minimizing, because then that point would have a dense horocycle and it would be contained in the orbit closure. So what I want to say is that if you understand the quasi-minimizing rays, you understand the interesting horocycle orbit closure. So it's a good first step to just understand what the quasi-minimizing rays are. So how much time do I have? I know I want to know how much time to spend on trying to explain this theorem.
About 40 minutes.
What? 20 minutes?
About 40.
40. Oh, okay, good. Okay, so let's briefly sketch proof of this corollary of this theorem by Berlin. And maybe I'll just state one direction. Proof of one direction theorem. So just to give you a taste of why these quasi-minimizing rays do give you non-trivial orbit closures. So let's assume sketch of part. Okay. So assume that ATG is quasi-minimizing. So let me draw it. I have this point. So I'm going to hide the surface, but this lives in a surface. And this is going to be, right, this is now ATG. And I'm assuming that this is quasi-minimizing, so this is at least, this distance is at least t minus a constant. Good. So let me give you a point which cannot be in the horocycle orbit closure. So look at the backside of this geodesic. So this is a minus, I don't know, a minus 2c of g. Okay, I want to go back enough. I don't know, this should be just a big number or a small negative number, which is smaller than c. And I want to explain why this cannot be in the horocycle orbit closure of G. So I have this horocycle, right? This is NG, the horocycle orbit of G. And let's assume by contradiction that it does get arbitrarily close to this point. So there is some NSG, which is very close to this point, which is way, way, way behind and past G. What do we know about horocycle orbit closures? What do we know about horocycle orbit? So let's draw the hyperbolic plane, and we have point G, and we have horocycle. Okay, we have a horocycle, and we have, this is NSG, and we know that the geodesic emanating from this point and the geodesic emanating from this point are asymptotic, right? Not only are they asymptotic, but if you wait far enough, you wait long enough, ATG, ATNSG are going to be arbitrarily close. So let me write this. The distance between ATNSG, this is true also in the surface, and ATG, this tends to 0 as t tends to infinity. This is the stable horocycle flow. Is this okay? You've definitely seen it. So this is just a property of horocycle, the horocyclic flow. Okay. So what does that tell us here? It tells us that if we want to, so if we follow this geodesic, now we have NSG, and we follow this geodesic, it might do something on the surface, and then it needs to catch up with this point. So this is ATNSG. It needs to catch up with this point. But this geodesic flow is at time 1. So what did we describe? We described a geodesic which is length t, right? This is ATNS, starting from way behind the point G and arriving at distance t minus c at the same time. Do you see the contradiction? I mean, the distance between, we've now found sort of a shortcut that makes the distance between this point, which is way behind, and this point, we found a shortcut which is of size t. This should be of distance. Yeah, I don't know. This should take much more time to arrive. Does this make sense? I'm I'm not sure I'm conveying the picture properly. So what I'm trying to say is that this cannot happen. So again, maybe I'll rephrase it. This geodesic here, this geodesic is essentially the most efficient that you can get up to an additive error. It's as efficient as you can get. It really escapes to infinity as fast as a geodesic can. And now I'm taking it way behind. I'm taking a point which is very far away. Maybe I can take, something much bigger than this 2C. I don't mind. I'm waiting way, way, way behind. And I'm saying that I can still catch up very far away. Does that sound impossible?
Is C in the definition universal? Is it universal?
No.
Because...
Oh no, it depends on this point. Depends on this point.
Okay.
Yeah.
Oh, it depends on the orbit or on that point specifically?
On the point. So if you take a different point, then if you take a point farther in, then this constant could be smaller. This constant essentially tells you, so the constant C essentially tells you how much time the geodesic wastes before it really gets efficient at escaping to infinity. It cannot waste time over and over, because then it will never, make it. It will never be efficient if it keeps wasting time along the surface, like winding around loops or not going in an efficient way, escaping from the base point.
But the point you pick, like A2CG, its constant may be bigger than the constant for G, right?
Yes, it should. Yeah, that's exactly the point. But what does it mean that I have this geodesic from almost this point, right, from NSG, which is very close to this A minus TD? I have a geodesic between this point and that point, geodesic of length T.
Yes.
It means that the distance between these, yeah. What do I want to? This is essentially the triangle inequality is what gives this makes this break, and I'm trying to see the triangle. So. Yeah, I mean, I think maybe I also made like a bad choice of making this into a 2C. Maybe I don't want to. I just think of this as being very, very large. So I don't know. T is just very, very large. So this point, right? This is the most efficient geodesic, and this point starts behind it, but still arrives at time t very far away.
But behind, they might just be close, like on the surface, because this orbit of G might be recurrent, might come back to G, like when T is large.
Yeah, but the geodesic shouldn't do that.
I mean, the orbit is a geodesic. Like when you write ATG, maybe ATG on the unit tangent boundary of the surface is close to G.
Yes, you're right. These 2 points can be close. What do I want to say? Yeah, I'm not conveying the picture well, maybe.
So the question is, he's thinking that like 8.
Yeah, I mean, there's a way to draw it in the universal cover. If you lift things in the universal cover, then this point here, or A minus TG, it's supposed to be a point here. And if your horocycle is very close, it means that there's a copy of this point here which means that you have a copy of your original G somewhere inside the horrible. Yeah, this is actually a point I want to be clear. So we should think of a good way of explaining.
Non, ok. Merci.
Ok, on continue.
Maybe we talk about.
Yes,
Yeah.
yes.
No, I think, sorry. So yeah, the point is, also my picture was that.
Maybe the point is that if the horocycle is close to the geodesic, it will cut the geodesic at some point. I mean, it's something like if the horocycle gets close to the geodesic, it will cut the geodesic at some point. Maybe it's something like it. No, it will.
It might. So wait,
And maybe this is the other horocycle that
my picture.
I mean, maybe this is the other horocycle that you have to consider, the unstable one.
No, I don't want to consider the unstable one.
But
wait, I think
at some point you have to do surely you have to do an intersection reasoning that something will cut a stable leaf at some point.
Wait, let me try to explain this again, because this is an important point. So wait, my picture was bad. I want a point, right? I'm assuming that that the horocycle orbit closure accumulates onto A minus TG. I'm assuming that. So I know that this point NSG is very arbitrarily close to this A minus TG. In particular, the geodesic. Let's give it a different color. The geodesic from here is going to follow the geodesic. This piece of the geodesic. It's going to follow it at time t. Does this make sense? So this base point here is arbitrarily close to A minus TG. So for time capital T, this orange geodesic is going to continue along the original one. So even if these 2 points are very close to one another.
I think you need to intersect the unstable.
Yes.
No. Wait.
Think to the case. You have cases where the whole cycle flow is minimal.
Yes,
In that case,
exactly.
not everybody follows the same trajectories.
They might get close, but at some point they'll get far apart. Because the stable.
Wait. Bear with me. I'll try again. Bear with me. Okay? What am I assuming? I'm assuming that my horocycle accumulates onto A minus T G. So I can get NSG arbitrarily close to this point.
Yeah.
In particular, I can get it close enough so that for time capital T, the geodesic emanating from this horocycle point, this orange geodesic emanating from this point, follows the exact trajectory of A minus TG for T time, right? Are you with me? This is T time. I can make sure that they follow together for T time. So the point in particular, this is going to be the point. Yeah. This is a T NS G is very close to G. You agree?
Yes.
Je suis pas spécialisé dans la géométrie.
Like even the understanding point when you say ATG and NSG are very close, they don't belong to the same stable. There is a part stable unstable that join them. And if there is a small piece of unstable, I think in the future you're gonna like you can be close at some point, but at because of the small piece of unstable you are going to
Yeah.
But I feel like I've lost you, and I actually want this point to be clear.
Okay, I think we should continue and we discuss after.
Okay, let me just try.
Yes.
Bear with me just one last time, and then we'll continue. Okay. I'll try. Maybe I'll do a new picture. So this is G. I have my geodesic. This is the point ATG. And I know that the distance between these 2 points, this distance is at least t minus constant. So these are very far away. And now I'm assuming that I'm taking the geodesic here, the horocycle here, and it's going to be close. So this is NSG, but it's also very close to a point A minus large T G. But these 2 points are close. These 2 points are as close as I want, because I'm assuming in contradiction that the horocycle accumulates onto this point. These 2 points are arbitrarily close. So for time capital T, I can make sure that these 2 geodesics follow the same trajectory. They're going to be arbitrarily close. They will follow one another for time capital T. So at time, so this is now going to be a point A capital T N S G, and it's almost just G. It's almost the same. These 2 points are almost the same. Are you with me so far?
Yes.
Yes, good. But what am I claiming? I'm claiming that if you continue, right? If you continue, you do something here, and now at a little t NSG, now these 2 points are very close. So this orange geodesic was little t long, but I wasted t time here. I wasted capital T time here. This part is capital T time. Maybe these 2 points are very close to one another. I just looped around for t time. I didn't do any progress here. For capital T time, I only went from NSG to this base point G. But now I need to catch up. This geodesic, the original one, this geodesic was essentially as efficient as possible. These 2 points are very far away. I cannot at time, so this thing, right, this is length little t minus capital T. I cannot make up this time between these 2 points. Does this make sense? I've sort of, but in this contradiction assumption, I found a shortcut on the surface that at time t minus capital T, I've went from almost G to almost ATG. Does this make sense now?
So I'm sorry to interrupt, but what I was saying is, as you're getting very close to NS, like to A minus T, as you're accumulating, what you're basically doing is that your horocycle gets longer. The horocycle that joined that point to G gets longer, right? Because
yes.
So
yeah. This is very long. This is something I don't know what's happening.
Yes,
here.
exactly. So this T will be affected. The final T you get to get them close has to be large or so.
No, it's the same T here. Oh, okay. Yes. You're right.
Because his NS
is wait along. Okay, fine.
Yes.
But this is true for all T, right? You're right. This little T for making these 2 points close to one another. Yeah,
Yes.
this might be very long, very large.
It might be very long.
But this is true for all little t. I can just wait that time. And now I found the shortcut. This again is t little t minus t for all t, right?
Mm-hmm.
I found the shortcut on the surface.
Okay.
Yeah. Okay. I mean, it's a good thing to be stuck on, because this is actually one of the key points I wanted to I think I really love this theorem by Eberlein and Darboux, and you know, I've thought about it a lot, and maybe I didn't explain it properly the first time, but I think this is a really key point. Moreover, it also has another component in it, which tells us exactly that those points that the horocycle can accumulate onto are exactly those points that you can now take a quasi-minimizing ray and still make cap to the original one. So understanding the loops and the shortcuts that you have on your surface can tell you what points on the horocycle can accumulate onto. So this is a point which you cannot accumulate onto, but there might be other points which you can. And those points would have some loops that do catch up. Okay. We'll now continue on. Unless there are some other questions.
No.
Good. Okay, good. So I will definitely not talk about the other direction, which is harder, and also beautiful. But so the other direction is saying that if a geodesic ray is not quasi-minimizing, then the horocycle is dense. Let's not talk about it. So let's go talk about Z covers. So, yeah. So Z covers of compact surfaces. So yeah, let's just first of all construct those. I don't know. Maybe you did talk about it, but so this is the surface of genus 2. Not a very nice avocado-looking surface, but I can take this surface of genus 2 and I can cut it along two non-separating geodesics, and now I can glue together. I can glue together Z many copies of this surface, of this surface with boundary left to right. So I'll just draw the boundaries. These are the boundaries. And I'm just gluing them, Z many copies of these left to right. And I get a Z cover. So, yeah, this is by Z. You have an isometry Z. You have a Z action, a deck transformation, acting by shift on this Z cover. And that's one way, at least, of generating. This is one example of a Z cover of a surface. So maybe one thing I want to remark at this point, you can talk about the representation. I mean, what is the fundamental group of this Z cover? So the fundamental group of this Z cover is going to be a normal subgroup of the fundamental group of your original surface with quotient Z. But one thing I do want to highlight is, so there are many hyperbolic metrics on, let's call this sigma naught. So this is sigma naught, and this Z cover is going to be sigma. So there are many hyperbolic metrics on sigma naught. There's a full Teichmuller space worth of hyperbolic metrics or representations or mark metrics. And once you have a hyperbolic metric on the surface, you can lift it to the Z cover, or maybe look at the induced representation on the normal subgroup, but you can lift it to the Z cover, and now you have a hyperbolic metric on the Z cover, where the Z action is an isometry. And again, since you have many hyperbolic surfaces to choose from on the compact surface, you have many periodics, so the same amount of periodic metrics to choose from on the Z cover. Does this make sense?
Yes.
There's
Yes.
a lot to say. Just briefly, this point, there are many metrics. I mean, you can maybe squeeze this neck of the surface to make it much longer. That would change the metric. You could make the gluing along here with a twist. That would change the metric. Good. And now, so let's consider this Z cover. I'll draw a bigger picture. And now let's try to consider a quasi-minimizing ray. So this is now just a point bracket G, and I have a quasi-minimizing ray. So maybe it's going to waste some time, it's going to do something for some time, but eventually it's going to be very efficient, and it's going to escape to infinity at the fastest rate possible. So this is G quasi-minimizing. Does this picture make sense now? Does this picture make sense?
Yes.
So this ray might waste some time looping around things, but eventually it's going to be very efficient at escaping to infinity. That's the only way. So there are two ways to escape to infinity on the surface, either to the right or to the left. And the idea is that in order to make sure that this quasi-minimizing ray only accumulates an additive inefficiency, right? It's very efficiently escapes to infinity, and I wanted to accumulate only an additive inefficiency. It means that after some point, if I look at the z copy, at some copy of the z action, this is some fundamental domain for the z action on the z cover, I'm going to see the quasi-minimizing ray being very efficient at traversing between the boundaries of this fundamental domain. It has to be very efficient. If it wastes time over and over again passing through these copies, then it's going to accumulate a linear error in the distance. Does this sentence make sense?
Yes.
Going to make sense.
Yes.
Good. So let me state a theorem. So this is joint work with James Farr from Leipzig, myself, and Yair Minsky from Yale. So in Z cover, so in the setting above, there exists a geodesic lamination. I'll explain what this is briefly. There exists a geodesic lamination, lambda naught, in sigma naught. So this is on a compact surface, such that all quasi-minimizing rays in sigma, so in the Z cover, are asymptotic to, well, the lift, let's call it to lambda, which is the lift of lambda naught. Let me draw a picture. So maybe I'll move the theorem. Okay, I'm not assuming that you all know what the geodesic lamination is, so I'm leaving this aside for a moment. I want to draw a picture first. So I have this pi z. I have this z map, right, to my compact hyperbolic surface, and I have the shadow of this quasi-minimizing point, right? I have, this is pi z g. And I can look at what this quasi-minimizing ray is doing downstairs in a compact surface. So it's going to loop around, and what did I do here? It's going to loop around, and then maybe do something like this, and then eventually it's going to be asymptotic to something, right? In this picture, it's going to do the same thing over and over, assuming that it continues looking like this over and over to infinity. It's going to accumulate onto some locus and on the surface downstairs. And this is my geodesic lamination. So this red, I don't know if you can see the red well, but this is lambda naught. And if I lift this upstairs, maybe it's going to look something like this. So this is going to be, the red here is going to be lambda, which is the lift of this curve downstairs. What is the idea? The idea is that this lamination, it's a closed geodesic invariant set. I'm going to give a definition in a second. It's a closed geodesically invariant set. And it tells you, for this particular metric, for this particular surface, it tells you what the most efficient routes are to traverse between the different copies, the different z copies in the z copy. This loop here is going to tell you what's the most efficient way to go between different boundary components of the fundamental domain for the z action for this particular metric on the surface. And in order for a quasi-minimizing ray to be efficient, to be quasi-minimizing, in order for a geodesic ray to be minimizing, it has to be as efficient as possible asymptotically, as efficient as possible at traversing these v copies. So it has to be asymptotic to this geodesic lamination. Is the idea clear before I briefly say what a geodesic lamination is?
Yes.
Good. Okay, good. So maybe just, digression, so definition, geodesic lamination. Lambda naught, sigma naught is a closed disjoint union of complete simple geodesics. So, in other words, it's a closed set. So it's a closed set, which I can decompose. It's foliated by geodesics, so I can decompose it into a disjoint union of geodesics which do not intersect one another and do not intersect themselves. So they are complete. They are full length, and they are simple. They do not intersect themselves, and they do not intersect each other. Is there a question? Okay, let me just give an example. So an example of a lamination. If you just have two simple geodesics which do not intersect, that's a geodesic lamination. You can add a leaf that maybe spirals around one on one end and then spirals on the other on another end. So this is a geodesic lamination having 3 leaves. I have 7 minutes, right?
No, you have 30 minutes. Because
How
we
much?
started late.
8.
30. Yes, 30. Yes.
Wait, say that again?
We have 30 minutes. 30. 0 and... Yes.
Oh, okay. 30 minutes.
Yes.
Oh, okay. Maybe I'll leave time for... Oh, okay, so I don't need to rush. Good.
Il m'a dit qu'il respecte le moment où il a commencé. Moi, je voulais
So,
respecter le calendrier. Donc,
maybe I'll make this bigger. Okay, so is this example of a geodesic lamination? Does this make sense? So just take a union of simple geodesics and then add another spiraling geodesic that spirals on them. That's an example of a geodesic lamination. Another example, which is more interesting, is, so I can't draw it per se, but I can draw an epsilon neighborhood of it. So it's going to be, maybe it's going to look like a closed loop, and then I'm going to have an arc going out, around, and then rejoining. So this is going to be an epsilon neighborhood of a geodesic lamination. This is a different example. It's going to be the Hausdorff limit of things of this form. So laminations which are called rational, which are just closed geodesic and isolated leaves. But what you should think of here, so again, this is an epsilon neighborhood of a geodesic lamination. If you look at the transverse here, if you cut it here, you will find uncountably many leaves. There's uncountably many geodesics. It's going to be a Cantor's worth of geodesics, so Hausdorff dimension 0. And they are going to wind around this loop, together for a while, and then there's going to be this switch where they can choose left or right. So in this counter set, some cylinder, some packet is going to go that way and then rejoin on the other end and continue. And you can construct these in a way that you will have, again, uncountably many geodesics that do not intersect one another and do not intersect themselves. Yeah, so this is, I don't know if how many of you have seen this. I encountered this, a few years ago. This has been extensively studied in hyperbolic geometry by Thurston, and these geodesic laminations on closed surfaces or on finite volume, finite area surfaces, they have a very rigid structure. They have a very interesting structure. So again, what do we have here? Let's try to recap. So we are on a mission to understand what the horocycle orbit closures are. The horocycle orbit closures, the interesting ones, come from quasi-minimizing rays. So we want to understand the quasi-minimizing rays. But understanding the quasi-minimizing rays, I'm telling you now that in the Z-cover case, all quasi-minimizing rays are going to be asymptotic. We're going to shadow a geodesic lamination. So if you want to understand the quasi-minimizing rays, you better understand this lamination. Does this story make sense? Good. Any questions about geodesic laminations that I can answer?
No.
Good. So let me give another theorem. So a coordinate follows from this. So again, this is with James Farr, myself, and Yair Minsky. So maybe I'll state it this way. One, this geodesic lamination lambda naught delicately depends on the metric. Of sigma or sigma. So, right, I told you that this geodesic lamination is going to capture the most efficient routes traversing between different fundamental domains for the z-action. If you change the geometry of this surface, you will change the different efficient routes traversing between the different boundary components. But changing the metric here would definitely change the lamination. Well, will change the lamination, at least in different parts of hypermolar space for different metrics. And there's a very delicate correspondence between this lambda naught and the choice of the metric. So in particular, what I mean by this theorem is that you can find two hyperbolic metrics on the topological surface, of fixed genus with a fixed topological z-cover. You can find two metrics which are arbitrarily close to one another. So they're just, one is a perturbation, arbitrarily small perturbation of the other. But the lamination is going to be very different. The laminations that correspond to these two metrics are going to be very different. So this is one thing. Second thing is that the structure of non-full, non-maximal horocycle orbit closures. So those orbit closures which are not everything depends on the structure, actually very much on the topology. Structure, even the topology of this lamination lambda naught. So for instance, I've described here two different types of laminations, one having finitely many leaves and one having uncountably many leaves. You can change the metric by just a bit. So this is a terrible picture now. let's give a better one. So maybe this is one. Yeah.
Or what?
Yeah.
What do you mean? What do you mean by non-maximal horocycle orbit?
Yeah.
Yeah.
So I just mean that it's not everything, not all of T1 sigma. So just a proper subset of everything, right? You have dense horocycles and you have the non-dense ones. I think Check, did you ask this question, right? I think maybe you call it irregular.
No, exactly. We have irregular. We have when you take a periodic orbit, orbit, it's not maximal.
Yeah, you're right.
Yeah, but I understand. But I understand on your paper, you want to, when you say non-maximal orbit, or you want to say irregular. What I know, we can
right.
on your paper, I think.
Right. So if you have a z-cover of a compact surface, then you don't have periodic orbits. You don't have orbits which are horocycle orbits which are periodic. So the only orbits which are not everything, the only orbits which are not dense are those which are irregular, have an irregular orbitals.
These orbits can be closed. The horocycle orbit is they are not closed.
No, okay. Never. They're actually never closed. No.
Okay.
Yeah, that's a good question. So that's sort of that was known. So maybe I should say that I did not talk. I promised to talk about geometrically finite setting. Maybe I'll. But okay, I'll say that now. So it's geometrically finite surfaces have either conical limit points, so geodesics which occur corresponding to geodesics which occur, or parabolic limit points which correspond to cusps which have corresponding periodic horocycle orbits. And this is an equivalent property for a surface being geometrically finite. Those are the only two limit points. So a z-cover, I was sort of rushing, maybe I shouldn't. Z-cover is geometrically infinite. It's of infinite genus. It's geometrically infinite. And therefore, we know that it has non-horospherical limit points. It has limit points which are neither parabolic nor, so they're non-horospherical and non-parabolic. So there's limit points which are not conical and not parabolic, and therefore they correspond to interesting orbit closures. And further, it was known that these can never be closed. So you can imagine a proper horocycle orbit. Maybe that was the question. You can imagine an orbit closure horocycle which is just properly embedded inside the surface. So it never returns to a compact set infinitely many times. That never happens in a z-cover. Horocycles and z-covers always return back to a compact set, and therefore they have interesting accumulation points. Thank you. Good question. I can't really hear. Sorry.
Yeah, I know that. So in the geometrically infinite case, you still have two cases of the trajectory horocycle orbit, and I mean if the closure of the trajectory, I think you noted the NR of G. This can be closed or not. I mean, it can be equal to its others or not, even in the geometrically infinite case.
Correct.
Not being parabolic.
In the z-cover case, that
they are never closed.
Where the orbit is closed, that is excluded.
So they are non-divergent. That's
right.
Okay.
I mean, they're not. I call them proper. I mean, they're not like proper orbits.
Okay.
You don't have that in z covers of compact surfaces. You don't have it, or in regular covers of compact surfaces. But you do have it in other surfaces. Definitely. Yeah. Does that make sense?
Yeah. Thank you.
Okay. Good. So I explained what I mean by 1. Maybe I'll explain a bit more what I mean by 2. So we spent some time understanding which points cannot be in a horocycle orbit closure of a point with a quasi-minimizing ring, right? You can't be very far back because then you won't be able to catch up. And I said that those points where you can accumulate to are exactly those points where you will be able on the surface to catch up back to your original quasi-minimizing ray. And in order to understand which trajectories are able to catch up with one another, since they all are asymptotic to this lamination, their correspondence between how efficient they can be catching up to one another, that comes from understanding the geodesic lamination. You want two very efficient quasi-minimizing rays to catch up to one another, up to some efficiency. And to study that, you need to understand the geodesic lamination. It's actually a pretty delicate analysis, and we're finishing it right now. But this is like the core idea. The core idea is that this geodesic lamination tells you what are the best routes. Maybe I could say another remark. So we have this geodesic lamination lambda naught. I'm saying those are the most efficient rays traversing between the surface. Actually, when you lift this to the Z cover, to lambda, all the leaves of the lamination, they still do not intersect. All the leaves here are going to be isometric copies of R. So these are going to be complete geodesics, back and forward times, and they are minimizing in both directions. That is, any 2 points along the geodesic, their distance is realized along that geodesic. These are exactly the most efficient route to go from that point at infinity to the other points at infinity. Right. And again, understanding that and the correspondence between the different possible leaves in this lamination tells you how horocycles can accumulate, what points horocycles can accumulate onto. So maybe I can expand on this. So actually, maybe this is part of a paper which was already out in 23, and we're now working on a sequel, which will hopefully be out soon, where we can we're actually writing down, we're giving a full description of all horocycle orbit closures in the Z cover setting. But in particular, there's a dichotomy. There's a dichotomy of non-maximal irregular horocycle orbit closures that either, so this dichotomy is actually a dichotomy on the surface, either one, all such horocycle orbit closures are countable unions, of horocycles, or two, they are not. So, or two, they all satisfy. Maybe I'll say they all contain a geodesic ray. I can say more. Maybe I'll say more. I have still some time, right? So maybe I'll say a bit more. But maybe I'll expand a bit. So, moreover, one happens. So type 1. This happens if and only if lambda naught is an isolated multi-curve, so is a union of finitely many closed geodesics. like in this picture here, just two closed geodesics. That's when type 1 happens, and that's our guess is this is the typical case. And 2 happens anywhere else. Yeah, else. So if you identify this geodesic lamination and you know that it is, so we call it a distance minimizing lamination, or it's also a maximal stretch lamination for some other geometric problem, which I won't have time to mention. So if this geodesic lamination is just a finite union of closed geodesics, then all the horocycle orbit closures in the Z cover are just going to be countable unions of horocycles. So they're not closed, but it's sort of close for them to be closed because they can only accumulate onto countably many other horocycles. And in the second case, they actually contain array. So maybe before going on, do you have any questions about this state of corollary? Maybe.
What about the closure of the orbit? When you take the closure of the orbit, what can you say so?
I'm talking about, so this is my shorthand for horocycle orbit closure. So this is the closure. Closure contains horocycles. Yeah, you take a quasi-minimizing.
No. It's okay. It's okay.
Yeah, okay. Yeah, in the case 1, you take a quasi-minimizing, so a point corresponding to a quasi-minimizing ray, you look at this horocycle. The closure of this horocycle is going to accumulate in different places. The closure of this horocycle is going to be just a countable union of horocycles.
So another question, if I understand correctly, from 2, so in the first case they cannot be minimal, and in the second case, because of the fact that there is an embedded geodesic ray, so there is a T, and you are saying that they cannot be minimal either way.
Yeah, they are never minimal. Actually, this was that result that they're not minimal, that was predated. I think also Alexander Bellis proved that, and others. Yes, so that was predated. It's maybe I'll. So again,
because I understand that the injectivity radius is always finite here in your set coverings, right?
Say that again.
You're saying the result of Alexander Bellis says that if the injectivity radius is finite, then they're never going to be minimal.
Here it's always bounded, right?
Okay, that's okay.
Exactly. But actually, we can say much more about that. So, yeah, if you did talk about Bellis's work, so I'll tell you a bit more. Maybe I'll just state one brief corollary, and then I'll tell you a bit more. So, corollary, all horocycle orbit closures on Z covers have integer Hausdorff dimensions. Dimension either 1, 2, or 3. So 3 is when it's dense in the unitangent bundle. In type 1, it's going to be one-dimensional. It's just a countable union of horocycles, countable union, dimension 1 thing. And here it's going to be two-dimensional. There's something to prove here, definitely, but this is a corollary that we draw. This, at least in this setting, they all have. I like to think of this in the context of the study of horocycle orbit closures in the context of rigidity of unipotent group actions. So one thing that we learn here is that there is no rigidity, right? The structure of the horocycle orbit closures delicacy depends on the metric, not on the topology. So if you change the metric by just a bit, the horocycles are going to look very different. So there's no rigidity on the one hand. On the other hand, you still recover some rigidity, at least in the sense that the dimension is always integer. But maybe I want to state something that will connect to your discussion about Bellis's work. So, right, you want to consider, maybe I'll call it this. So you want to consider this set, which is all those T and R, such that the horocycle orbit closure intersects for which ATG is contained in NG. Wow, this is confusing now. Right? You talked about this? Right? You have this point G, and you have this ray, and then you're asking the horocycle, where does it accumulate onto the ray? Right? Which points ATG does this horocycle accumulate onto? Right? You talked about this this week? Yeah. So what we show is that this is a semigroup. It's always closed, non-discrete semigroup of R, of 0 infinity, of positive numbers. So this is always true. And for case 1, for type 1 surfaces, this is countable. And for type 2, this contains a ray. Possibly, so we have examples where it's just the entire ray. And this is part of the analysis. I mean, part of the analysis is understanding exactly. So, okay, maybe I'll say this. Right, I said the type 1 surfaces are those where the lamination is just a finite union of closed geodesics. That essentially means that if you want to accumulate onto a point here, you would have to find a geodesic which wastes some specific amount of time and then catches up with the original ray. So there's some inefficiency S here that has to happen. And because the lamination is an isolated multicurve, this S really has to come from the topology of the surface. And this topology is countably generated, finitely generated, right? So if you look at S of you're looking for a particular S. I'm saying S, but this is actually T. So you have some inefficiency, and this inefficiency is going to be T corresponding to this T here. And this T will come from looping around somewhere in the surface of length T, and there are only finitely many possibilities of doing this. And this analysis eventually gives us a countable semigroup, countable set of points where you accumulate onto. And if your geodesic lamination is more complicated, you can actually get a ray. You can get many, many more ways of catching up. I don't know if this made much sense at this point, but hope at least it resonates with your discussion about Bellis's work. So at this point, I'm not sure. At this point, I'm probably done, right?
Okay, let us thank Mr.
Thank you.
Okay, is there any question?
Maybe just a general question, because I'm coming from a different background. So can you do these type of studies in variable negative curvature, not hyperbolic?
Yeah, that's a good question. And I don't have a good answer.
Okay.
So I do not know very much about variable curvature.
Okay.
But
I just wanted to know, like, if there's something now, there are some results, or...
No, not that I'm aware of. I'd be happy to see.
Okay.
But no, not that I'm aware of. I can say that you can consider two things. Yeah, I don't know. It's not really related, but what we are considering Z covers where the Z action is an isometry.
Mm-hmm.
You could look at quasi-periodic covers and things like that. It's not varying the curvature; it's varying the metric, and that also could make for problems. It's a different question. I don't know.
Okay.
But associative, yeah. So to your question, I'd be very happy to see it, and I'm not thinking of it at the moment.
Yeah. Here another question. Once you fix the covering, if I understand well, you have some sort of embedding of the Teichmüller space of the base into some Teichmüller space of this infinite surface.
Right.
Can you say something about what happens if you have a metric which is, say, close to the embedding of this Teichmüller space? Or things get wild, or yeah.
Yeah, that's a great question. Yeah, that's exactly what I was sort of hinting at when I said quasi-periodic Z cover. So you could take a topological Z cover, right? And then you're looking at a point in Teichmüller space which is not fixed whose metric is not fixed by the Z action. So it's not exactly in this embedding, as you say. And I do not know exactly what happens there. Our analysis really breaks down. It really uses, our particular analysis breaks down, but I'm optimistic that one could definitely say things about it. We really use this reduction down to the compact surface to solve this geometric problem of what are the most efficient rays. This is a geometric problem that could be stated in a very different language about best Lifshitz maps to the circle and the maximal stretch locus of best Lifshitz maps, etc., etc. We really use the structure and machinery that has been developed by others also to analyze this question. And once you have a quasi-periodic surface, that reduction really is not exactly there, and you need to be much more careful. So I don't know. This was already delicate as it is, and I don't know. But I'm optimistic that one could be able to say this.
Yeah, and maybe a second but more natural question. What does it, what about C2 coverings or higher rank coverings?
So we're working on it. It's really interesting, actually. We're working on ZD covers now, on abelian covers now. And yeah, we can already say a few things that you still have some sort of a reduction to elimination and things like that, but we're still in the midst of it. And I can say that things that were just a nuisance in the Z cover setting. So for instance, I told you that you could have in the lamination like an isolated leaf. So maybe two closed geodesics and then an isolated leaf between them. That was a nuisance in our analysis in the Z cover case. When you have these in a Z2 cover, that nuisance becomes a real problem, which we still are trying to figure out. But yeah, that's a very natural question.